Okay, I think we can start now. There are some people also joining by YouTube.
Okay.
Okay, we'll introduce first in Spanish and then in English. So, bueno, a ver. Bueno, buenos días a todos y a todas. Es un placer muy grande para... Okay, there is a problem here with the audio. Okay, we'll introduce first in Spanish and then in English. So, bueno. Okay, now I think it's okay. Bueno, es un placer muy grande para mí presentar hoy el seminario sobre software y hardware abiertos, la comunidad de los modelos de negocios y el licenciamiento, que está a cargo de uno de los más grandes expertos a nivel mundial en licencias open source, como es Andrew Katz. Welcome to everyone. It's a pleasure to present Andrew Katz today, who will give us a very interesting seminar on open source hardware and software, the community, the business models, and licensing. Andrew Katz is one of the most important experts at worldwide. He's a lawyer from London, UK, and he is specialized in open technologies, and he has advised many companies, governments, and also research organizations on open technologies. For example, among different companies, he has advised, he had worked with Canonical, the company behind Ubuntu, and also Red Hat. And in terms of open hardware, he's one of the co-authors of the CERN open hardware license. So it's a great pleasure to have him today. We would like to thank him for accepting giving this seminar, for accepting the invitation. And we are looking forward to learning a lot about open licenses from him. So thank you, Andrew.
Gaston, thank you very, very much indeed for inviting me. It's a huge pleasure, and hello everyone. So if you will bear with me for a moment while I share my screen, then hopefully we can get started. So let's try this. Right, how's that?
Great.
Excellent, thank you. So let's start at the beginning, and the fundamental question is, what is open hardware or open source hardware? I don't get particularly excited about the distinction between the two, so I'm not going to talk about that. I think in most contexts it's pretty clear that they're the same thing, so I don't intend to talk about the distinction, but just to let you know that we will come across different terminology. Some people call it open hardware, some people call it open source hardware, but to understand what open hardware is, then you need to understand what open source is, and I'm sure you're all very familiar with that, so I'm going to run through a very brief recap. So if you go with the definition of free software, which is broadly the same as open source software, it's software which anyone can use, study, distribute, and adapt. And in order to make use of that software, you have to have access to the source code as well. And by way of context, 80% of code that's developed at the moment is open source. Open source is everywhere. It runs phones, so Android is an open source operating system. But having said that, iOS on the iPhone contains a huge amount of open source as well. It runs internet devices. Many cars run on open source software. You'll find it in appliances. Currently, 100%, every single one of the world's top 1,000 supercomputers is running some variety of Linux. And from a commercial perspective, IBM bought Red Hat for $34 billion. Red Hat is obviously a very prominent open source company. So open source software is very much in the mainstream. And the question is, why is it so popular? Why is it so successful? And really, the main reasons are, well, it facilitates collaborative research and development. Anyone can get involved in an open source project very easily. It enables organizations to focus their resources on differentiation. So in the marketplace, they're competing through the things that make them different from their competitors. Nobody's going to buy from a particular company because it's using a specific sort of database. They're much more interested in what sits on top of that database. So as a result, there's no point in companies differentiating themselves from each other just simply because they're using a different sort of infrastructure. And that means there's no reason for them not to collaborate in improving the infrastructure, which is why successful open source software projects are often infrastructure projects. So it means that you're not reinventing the wheel. You're not putting effort into creating something that somebody has already created. And it facilitates the use of the open source development methodology. Well, what do we mean by that? In fact, there's a lot of different ways of developing open source. But the most common way that happens these days is to use some sort of collaborative mechanism like Git, so GitHub, GitLab, for example, and that makes it extremely easy for anyone with an internet connection to be able to access an environment that enables them to develop software in collaboration with other people. So how does that map onto hardware? Well, using a similar definition, it's hardware which anyone can use, study, distribute, and adapt. And the design materials have to be made available under a license to allow this to happen. And examples of open source hardware would include electronics, and that would typically be circuit boards and the components on them. Silicon chips are becoming an increasingly prominent area where open hardware is used. But it could also mean much more physical things like cases or racks or furniture in a server room, for example. All of those can be released under open hardware licenses. You can even have mechanical devices like motors, engines, cars, boats. All of those can be available on an open hardware basis. It can cover 3D artistic works. It can cover 3D printed works. It can even cover fluids. So, for example, if you have some sort of hydraulic device, it might need a specific sort of hydraulic fluid to work properly. And then the recipe for that fluid could mean that the fluid becomes open hardware if it's released under an appropriate license. So essentially anything that exists in some shape or form in the physical domain as opposed to the digital domain can be available under an open hardware license and can be open hardware. And there are a number of different definitions as to what open hardware can be. So, for example, the Open Source Hardware Association produces some guidelines which are based on the Free Software Foundation's 4 freedoms, and also the 10 criteria which the Open Source Initiative uses to define what they mean by open source software. So based on that, they state that open source hardware is hardware whose design is made publicly available so that anyone can study, modify, distribute, make, and sell the design or hardware based on that design. And you'll recall that that's very similar to the definition of free software, which is presented by the Free Software Foundation. So let's pose a question. Can, for example, a chocolate cake be open hardware? So a chocolate cake, you obviously make that to a recipe. A recipe is a set of ingredients and a set of instructions on how to combine those ingredients in order to create the cake. So is that recipe a design document? Well, let's go back to look at some legal principles. Software is automatically protected by copyright. Therefore, in order to open source software, you need some sort of license. So by that, I mean that in any way that you want to use software, then you will need permission to do so. Because if you don't have that permission, if you don't have that license, then you will likely be breaching somebody's copyright. Is that always the case as far as open hardware is concerned? And the answer is not necessarily, and I'll go into that in sort of slightly greater depth. But one of the things that we have to consider when talking about open hardware is the sort of intellectual property rights that apply to that hardware. With software, it's relatively straightforward. We're almost always talking about copyright. We may be talking about patents as well, but generally speaking, we're talking about copyright, and that makes open source software a much simpler regime to operate in than open source hardware. So one of the issues is that the intellectual property rights which exist in a particular work vary from jurisdiction to jurisdiction, from country to country. So, for example, in terms of fashion, Italy has much more stringent laws on the protection of fashion designs than the UK does. And similarly, with database rights, the European Union has a specific right which covers rights in databases, and means that if you want to make use of or extract significant amounts of that database, you need to have a license from the database owner, whereas in the United States, similar rights do not exist. So this is one of the challenges we have to consider when we're looking at open hardware. Copyright law is pretty much harmonized at a high level throughout the world. That's certainly not the case as regards a number of different intellectual property rights. So the challenges that we have in terms of intellectual property are that open hardware can cover a broad range of different rights. We've already talked about copyright and patent rights. There may also be design rights, and these vary significantly from country to country. So in the UK, for example, we have both registered and unregistered design rights. And in fact, even though we've been subject to Brexit, we are still subject to additional design right laws which emanate from the European Union, and there's another 2 sets of registered and unregistered design rights. So we currently in the UK have 4 different sets of design rights which apply potentially to any form of hardware. We have some very specific, strange sort of rights which are unconnected with the others, like plant breeders' rights. We also have semiconductor topography rights, which are sometimes called mask rights, and they cover the specific layout of silicon chips. And then there's also database rights that we've talked about. So there's a huge range of rights that we need to consider. So openness implies freedom. So once you have a license under the various intellectual property rights to do these various things, then that means that you really, that's the connotation of the word openness, means that we're allowed to do those things. But that doesn't mean that the license that we're going to be granted is completely without restrictions. And there are broadly 2 different types of licenses that we're talking about in both the worlds of open source software and open source hardware. And that is academic or permissive licenses. And basically, if you have to design under an academic or permissive license, you have very few obligations which apply to it. You can make free use of the design, do with it virtually anything you want. You can incorporate it into proprietary design, for example, without any problem. And the obligations that apply are relatively straightforward ones. All you have to do is to retain things like attributions and copyright notices, for example. Sometimes you might have to supply some license text as well, but it's very easy to comply with. And crucially, you do not necessarily, if you are passing on some software or a product which is derived from a design which is released under one of these permissive licenses, you do not have to pass on the design documents themselves, the source code itself. In contrast, we have what are called reciprocal or copyleft licenses. Sometimes they're called share-alike licenses as well. And if you make use of material which is licensed under one of those licenses, you have to, if you are distributing the product, so in the case of software, it would be object code. In the case of open hardware, it could be a physical object, for example. If you're using a reciprocal or copyleft license, then you would also have to make available to the recipient of the product the original source code or design materials that relate to it. So there's the two major distinctions between the types of licenses that we would have in the worlds of open hardware and open source software. Now, with software, the reason that this regime works well is that there are many chances for copyright to apply. So anytime you're using a piece of software, whether you're running it or whether you're distributing it, whether you're downloading it from somewhere, whether you're modifying it, any of those activities means that you are carrying out some sort of act which is generally prohibited by copyright, and therefore enabled for you to enable for you to carry out that particular act in a lawful manner, you have to have permission. And when we're talking about permission, we're talking about licenses. So every time you do one of those things, you're going to need a license to do it. And every time you have a license, there is an opportunity for conditions to apply to the use of that license. So this is what makes those obligations that I talked about, the requirement to retain attributions, the requirement to provide a license text, or in the case of copyleft or reciprocal licensing, the requirement to provide the original design or source code. All of those are conditions which apply to the relevant licenses, and because so much of what you do will require the use of a license in the world of software, there are many opportunities for that condition to apply. That's the situation as far as software is concerned. So it's not necessarily true as far as hardware is concerned. So for example, every time I make use of a hammer, I don't have to get somebody's permission to do that. I can just hammer in a nail. I don't need a license to do it. And that's one particular issue that we have in the world of open hardware, is that this necessity to have a permission does not apply so often, so there are fewer opportunities to apply these conditions, like having to provide the original design materials or retain attributions, etc. So we need to be aware of that. So what licenses exist? Well, free and open source software licenses you may well be familiar with. There are the BSD, MIT, and Apache licenses. Those are all academic or permissive licenses that that allow you to make very free use of the materials that are licensed under them. And then there is the GPL, otherwise known as the GNU General Public License, which is a reciprocal license. So it has this requirement of, if you are shipping software which contains GPL code, you have to make the source code of that software available. There are also content licenses out there. So you may have come across Creative Commons licenses, for example, and there's a whole family of those, and they're generally used for a variety of content, like music, like text, like photos, like videos, etc. So they're aimed much more at content than they are at software. And then we have licenses that have been written specifically for hardware, such as the CERN open hardware license family. There's a license called SolderPad, which is based on the Apache software license. There's some other ones like Tapper, OCP, and there are varieties that are permissive, and there are varieties that are copyleft. So let's talk about a few issues that we have in relation to open hardware, and particularly in relation to openness. So if we talk about an understanding of the distinction between software and hardware, I mean, software is ultimately made of data. It's made of numbers. It's made of binary digits of ones and zeros. So any piece of software just consists of a pile of ones and a pile of zeros combined in a certain way. And hardware is made out of atoms. So if you have source code and you compile it, and the source code is essentially the instructions of how to make a piece of software, then ultimately you will get to an executable or a binary, and that's basically your ones and your zeros. So you're getting down to the most basic elements of what you're creating. By taking the source code, running it through a compiler, you will get a binary or an executable consisting of these ones and zeros. And that's what we understand when we're talking about source code. But with hardware, it's not quite as straightforward, because we do not expect the instructions that you are provided with to make a piece of hardware to explain in great detail how you have a bunch of atoms and they're combined with each other. It's not as if you are 3D printing a hammer using individual atoms of iron and steel, for example, to make the hammer head. We know that the hammer is made of existing materials and components. And this is even more obvious if you're talking about how to make a piece of electronics, for example. You'll need to have the design of the circuit board, and then you will also typically get a list of components, and we'll be talking about things like resistors, capacitors, and so on. And the instructions, you would just expect it to say, okay, you need so many of this particular resistor, it's 330 ohms, it's a particular physical size, it's got a certain power handling and several other characteristics as well. But we're not expected to understand how to make the resistor, because it's a readily available component that you can buy from any electronics supply organization. So one of the things that we always have to tackle is, how deep do the instructions go? At what point are we able to say it's okay just to specify a component and expect the person making that design to go and get the component, rather than have to include the instructions of how to make the component from scratch from its constituent atoms? And if you don't have all of the instructions that enable you to make the resistor from scratch, is the design truly open? So this is one of the things that we wrestled with in great depth when we were talking about the CERN Open Hardware license. And one of the ways that we dealt with that is to introduce the concept of available components. And an available component is anything which you are able to source and which you have all of the appropriate information and specifications necessary to be able to source it. And that may, and it's quite probable that in order to get that component, you may have to pay for it. That's fine. Nobody's expecting people are going to be giving resistors and capacitors away for free. And it may also be the case that those components are proprietary as well, meaning that we don't necessarily have the open designs available to make them if we want to. So CERN OHL addressed the reality of life. They understand that when many open hardware projects, it's necessary to be able to source the materials and to be able to purchase them. They may be proprietary themselves, so an open design may contain proprietary components. This is not the case in open source software. An open piece of open source software has to be software where the design for everything is made available, including all of the components, the libraries, etc. If it doesn't contain all of the source code for all of that material, then it doesn't qualify as open source software. So that's a distinction between open hardware and open source software. So there's a number of other issues that we have to consider. One of the questions that comes up very frequently is a question of field of use. So people occasionally try to use something like a Creative Commons non-commercial license to release an open hardware design. One of the issues with that is that the Creative Commons non-commercial license is not open source. It's not open source hardware, and it's not open source software if it's released under a non-commercial license, because the definitions of both open source software and hardware require that the design is available to be used in any field, whether the field is commercial or not. So one of the things to watch out for when you're considering open hardware licensing is, and sometimes people do release open hardware designs under Creative Commons licenses, but you have to ensure that Creative Commons license used is not one of the non-commercial variants, because if it is, then that is not open source hardware, because there is this field of use restriction in there. And likewise, we need to consider other potential IP restrictions, even though you believe that you have all the rights because you've got the design under a license like the CERN Open Hardware license. There may actually end up being other rights that you need as well that are not licensed under that license, possibly because the underlying rights are actually owned by somebody else who hasn't licensed them to you. So a classic example of that is patents. So that's just something that you need to be aware of. So in software, if any piece of software is released as source code under a license which is approved by one or both of the Open Source Initiative or the Free Software Foundation, then you can call that software free software or open source software. It's not quite as straightforward in the world of hardware. So one thing to be aware of, if you look at the Open Source Hardware Association definition, is that, first of all, the design has to be made public. Now, I don't want to get into this in too great a depth, but it's perfectly possible for you to release a piece of software under an open source software license and to distribute it privately to somebody else without it ever being made public. And that's open source software. That's fine. If I create a word processor, and if I transfer it to my friend and I make it available to my friend under the GPL, for example, then I've provided my friend with a piece of open source software. Now, I'm not allowed to put any additional restrictions on that to say that my friend can't then go and distribute the software to the world. That's fine. If they want to release it to the world, they can do so. But one of the things that the definition of open source permits, and indeed a lot of the drafting that goes into licenses like GPL version 2 and GPL version 3, is to permit this private distribution from person A to person B without ever making the software public, as long as person B, if they decide to do so later, are able to make it public themselves. That doesn't apply to open source hardware. If you follow the open source hardware definition, in order to call a piece of hardware open hardware, then you have to make the design to it public first. And it's what generally people do anyway, so there's nothing unusual there, but there isn't this ability to have private distribution. In addition, the interfaces to any software contained within the open source hardware must be documented, or the software itself, which is contained within the hardware, must be provided under an OSI license. So an awful lot of hardware will consist of a combination of hardware and software. For example, something like an Arduino, which is a small microcontroller, will obviously consist of the physical circuit board and the chips, etc., and components that are contained on that, and that's available under open source hardware terms. But it'll also contain software such as firmware, etc. And in order to qualify as open source hardware, the software that is incorporated within an Arduino must either be itself made available under an open source license, or at the very least, all of the interfaces must also be made available. There's also a certification scheme available under the Open Source Hardware Association, and that requires that any open source hardware design has to use open and non-proprietary components where possible. So with hardware, it's not quite so easy to apply a definition of openness. And we did a study for the European Commission a couple of years ago. So I was involved in a consortium consisting of the organization called Open Forum Europe, and with some people from Fraunhofer Institute in Germany as well. And we looked at the context of innovation, openness, and economic impact of open source software and hardware within the European Union. And one of the things that we developed was a taxonomy for placing projects on an openness spectrum. So as well as looking at the openness of the underlying design materials and which license it's released under, we also looked at a number of different criteria involving the ability for people to become involved in a specific project, and also the way that the project is governed as well. I'm not going to sort of delve in that in any greater depth, but feel free to ask me about it later, because I think we do have a question and answer session later. One of the other things that we looked at in the context of that study was something that we called the hardwareness spectrum. So I mentioned that there's a number of different things that can be released under an open source hardware license, and that ranges from things like chips, and just to sort of go on a sort of brief digression here. So the way that silicon chips are often developed is that essentially a silicon chip is a collection of logic gates, so AND gates, OR gates, NOR gates, etc., which are combined in a certain way. And the way that these gates are combined can be described using something called a hardware description language, and a hardware description language can look extremely similar to an open source, to software, whether open source or not. So a piece of code written in a software language is obviously something that's written using a text editor or an integrated development environment. Exactly the same system and process can be used to create a silicon chip within within a hardware environment. So the development process for developing a silicon chip and for developing software are very similar. They involve a developer sitting at a computer, typing in something that looks like code into a text editor or a development environment. In the case of software, then in order to generate the software, you go through a tool chain, which basically consists of taking the source code, putting it through various components like a compiler and a linker, and the output is something which is either a binary or an executable, and then that is the product basically. If you're designing a silicon chip in this way, so you might be designing a processor chip, for example, then you would do so in a very similar way. You would write the code for the chip, which would describe how the various logic gates interconnect with each other, and then you would put that through a tool chain, which would essentially produce a binary object which could either be fed further into the silicon chip development process, and it would end up with a design which goes to a chip foundry, which can then produce the silicon chip, the physical chip. Or a very interesting development is the production of a sort of chip called an FPGA, which is a field programmable gate array. And essentially what that is, it's a blank chip. It's a chip that can be loaded with a particular description of all of the gates that go into it. And when you configure an FPGA in this way with a piece of code that goes in and does this configuration, and it's called a bit stream, then the chip will actually become the chip as defined by the bit stream. So for example, this blank chip, it could become a processor chip, or it could become a memory chip, or it could become some sort of interface chip for something like networking or USB, for example. So this blank multi-purpose chip can very easily be configured to enable it to fulfill any one of a number of functions. And we're talking about a silicon chip here, so we're talking about about hardware. So we describe that as something that is being very soft, because it's many ways it's almost indistinguishable from software in the development process is very similar. Environments like GitHub can be used to develop chips in this way, and so on. There's very little distinction between them. Something that's a little bit harder on the scale of soft to hard is a circuit board. So if you get a design for a circuit board, you can potentially make one at home or in the laboratory or whatever. That's a relatively straightforward process. Even more quickly, you can quite often just take the design files, send them off to a specialist producer who has all of the equipment, who will generate those circuit boards, and they can send them back to you immediately, and you can have one off, or you can get to make 10 of them, and this can be done very quickly. There are some services, depending on which country you're in, that can turn around your circuit board, custom circuit board design, within 24 hours. It can be done very, very quickly indeed. Something much harder is something like a motor vehicle, for example, and that has much more complexity involved. In order to build a motor vehicle, obviously you're going to be spending months in a workshop. You're going to be using a lot of equipment like presses and milling machines and lathes and so on. You've got to be handling a great deal of physical materials like sheets of steel and so on. So we regard that as being something that on this hardware spectrum, as soft to hard, we regard something like a motor vehicle as being very hard. And the relevance of that really comes in when we have a look at this cycle. And if you're looking at the design, so the process is essentially that you will take a design, which could be the source code of a piece of software, then you build it, and by building it, you'd be putting it through your compiler and linking process. And then, so once you've got the binary, you'd be able to run it, which would enable you to test it. And then you make any changes that were necessary as a result of the testing. And then you basically go back to the design phase, making the changes that you believe are necessary. Then you can go to the build phase, test phase, and so on. And in the world of software, this can be an extremely rapid process, and it can be run simultaneously by any number of people using tools like GitHub, GitLab, etc. So that's a characteristic also of something that is very soft on the software to hardware in a spectrum. So similarly, if you're designing something like a silicon chip, you can create your initial design of source code. You can build it using your FPGA design tools, and then you can test it by loading it into your FPGA, which takes a couple of seconds, and then you test it to see if it works. And any issues that come up, you go back to the design phase and make the changes that are necessary. And in both the cases of software and hardware, when you're happy with it, then you'll go through a productized process, which basically means that you will make it available for shipping to the customer. Now, in the case of something like software, productization may be extremely straightforward. It may be just a question of making a download link to your binary available on your website, putting it into some sort of installer package and making it available. On the other hand, if you're talking about something that is much, much harder, like if you're making an open source car, for example, then productize is going to involve basically building a factory, figuring out all of the production engineering aspects of how to put it together. So you're talking about the distinction on the one hand with software, the costs and time involved. It could take a couple of dollars and take a matter of minutes to productize something. In the case of something that's very hard hardware, it could take many years to completely productize something, and the costs involved could easily be billions. So there's a huge distinction there. And if we go back to the idea of chips again, so we're talking about, we were talking initially about FPGAs. So the design, build, test cycle can be very rapid because it's almost exactly the same as software. But what if you want to create a chip that is not the same as an FPGA? So if you want to create a chip which is a native processor chip, for example, because you're ultimately going to be sending the designs off to a foundry, which is then going to be creating these chips in bulk, thousands of them, tens of thousands, hundreds of thousands, however it may be, however many it may be. You can still do most of this process in silicon, and digitally in your whole design suite using your computer, and whereas you can't necessarily build your silicon chip in that case, and these are called ASICs, by the way, which is an application-specific integrated circuit. So ASICs are any chip that isn't an FPGA, essentially. What you can do, there are tools available that instead of meaning allowing you to build, you can simulate. So almost all the characteristics of a chip can be determined within simulation software, and that includes the amount of current they use, thermal characteristics, how hot they're going to get if they're carrying out various activities, the speeds of the various parts of the chip, how quickly you can run it, how quickly signals will propagate from one location to another. So by the time that you have produced the design materials entirely within this design, simulate, test cycle, you will be pretty confident that it is going to do exactly what you want it to do when you finally send it off to production and get the design turned into real physical silicon chips. And this simulate cycle is also relevant to many other areas as well, but it's a long way to go. I mean, for example, many parts of a car design can be carried out entirely within the digital realm, within computers. So there are many tools available to enable you to predict the behavior of certain suspension settings, or to predict how a car will react aerodynamically, for example. But it's not possible yet to be able to create an entire car and all its mechanical and electronic components, and to be able to simulate that in a way that you can produce all of the design materials knowing that it's going to work, and then you can send that off to productization. So there's always going to be, in the case of something like a car, a lot of physical activity involved in the test cycle. So we found, when we were doing the European Commission study, that if you're working in the domain of softer type of hardware, then the community surrounding it acts much more like a software project. So there are plenty of processor designs that are available as open source hardware. Many of them are available on GitHub or GitLab, and they typically use as their basis something like an instruction set architecture, which is defined by RISC-V, which is an explicitly open source instruction set architecture. And there are vibrant development communities around these, as there are between development communities involving many pieces of software as well. And the dynamics around those are very, very similar. However, for harder hardware, we tend to find that these, and the designs for them is only released at the point when all of the development has happened within that organization. So whereas with open source software, and also with the very soft end of hardware, so silicon chip design intended for ASICs, for example, the designs can be released in a relatively buggy version, and then the community will develop around that particular design to enable development to be continued, to enable collaboration, to deal with bugs and so on. That's not necessarily the case as far as the hardware is concerned. And we interviewed a number of organizations. For example, we spoke to people from Arduino, and they very much have this concept of open when ready, which is some terminology that comes from a sort of very good paper which has been released. I'll give you some details of that later, but Bowman and Sterling. And there's a distinction here between the way that soft hardware is developed and hard hardware. And when thinking about developing a community, it's important to think about at what stage, what point on that spectrum of software and hardwareness your particular hardware design is going to be. Can copyleft or reciprocity work in open hardware? As a co-drafter of the CERN open hardware license, I'd like to think the answer to this is yes, but we can't be quite so confident that it works quite so well in hardware as we are with software. And part of the reason for that is what I was talking about earlier, is the number of opportunities that you have for conditions applicable to licenses to apply to the use of hardware as opposed to the use of software. So the main issues are, first of all, there's this impingement problem, what I've just talked about, the problem that many uses of hardware do not necessarily require the use of a license, and it's only when you have the use of a license that you can apply these various conditions that mean that this reciprocity principle, the principle that the design has to be made available, can apply. So that's one issue that we have to think about. We also have something that I call the boundary problem, and this applies both horizontally and vertically. So we've talked about the vertical issue when we were talking about available components within the CERN open hardware license, and the answer, well, the fundamental question that we have here is, if you have an open hardware design, does that mean that you have to provide the instructions that for how to make each individual component, essentially all the way down to atoms? And we've come to a particular solution for that using this idea of available components within the CERN open hardware license. But since from a practical perspective, the answer to that has to be no, you don't have to provide all of the instructions in order to make everything from atoms. Just logically, open hardware wouldn't work if that was a requirement. The question is, okay, so where do we draw the line? And a similar issue applies as far as horizontally, as far as assemblies are concerned. So for example, if you're thinking about a car, if you have a suspension assembly which is available under a reciprocal open hardware license, then does that mean that the second that I bolt that suspension assembly to the rest of the car, does that mean that the whole of the car then has to be released under an open source license? And does all of the design documentation have to be made available? And there's a number of different ways in which that's dealt with. But again, there has to be a boundary here because otherwise the concept of open source hardware just wouldn't work if there was an obligation to provide all of the design materials for anything that you attach a component to that itself is available under an open source hardware license. And so we talk about this. There's an article that I've linked to on this slide. So in terms of development issue, I mean, we've touched on this before, but in the whether you're available under an open source licenses. So example is.
Sorry, Andrew, I think there is a problem with the connection.
Is cheap computer as long as you have access to the internet in order to enable you to participate in things, processes like GitHub, GitLab, etc. With hardware, it's a lot more complicated. So first of all, there's very little open source development hardware of software available. There is some, and there's an increasing amount, but at the moment, not a huge amount. And also, depending on the hardness of the hardware, you're likely to need complex and expensive physical tools. So, you may need lathes, you may need milling machines, etc. And then, of course, once you've made a piece of hardware, you're going to have to ship it somewhere as well. For something like a silicon chip, that's pretty straightforward. They're small and light. But for something like an open source dump truck, that's going to be much more complicated. You need to think about the space that you need. If you're developing an open source dump truck, you're going to need a large factory. And it will also have to have various environmental constraints as well. If you're making silicon chips from scratch, you're going to have a space that has very specific environment. It's going to have to have certain humidity levels. It's going to have to be very low on dust, for example. And then, of course, when you're talking about any piece of hardware, you need to think about the feedstock, and by that I mean the materials that you're using. So, for example, in the case of an open source car, you're going to need a whole load of sheet metal, probably steel, and then steel comes in a number of different grades and qualities and thicknesses and so on. So you're going to need to have specifications for all of those available to you as well. So the concept of developing and building hardware is a lot more complex than it is for software as well. So as we said, there's a picture of an FPGA there. If we are talking about developing for FPGAs, then that is much more like software. So we've talked about the hardware scale earlier, and one of the things that we build on in the European Commission report, and I can find a link to that as well. We expand on this somewhat and talk about how that works, but it's a useful tool to have available in terms of thinking about how you're going to develop and make an open source hardware project available. One other potential issue we need to think about is the economic impact as well. So if you want to replicate the Linux kernel, it literally is just a question of taking a binary and replicating it in your computer, and that just requires one very simple command. It takes a few milliseconds and the job is done. If you want to replicate a car, then that is automatically going to cost you, at the very, very least, tens of thousands of pounds, dollars, euros, whatever. So that is automatically an expensive process. Somewhere, at the cheaper end, the cost to replicate an FPGA can be as cheap as $1. They're very inexpensive. Obviously, the more complicated ones are more expensive than that, but the cheapest cheap FPGA that you can get your hands on is around $1. So again, this sort of emphasizes how close to the concept of open source software chip development in open source hardware can be. So I'll just give you an example of sort of the impact of this. As far as open source hardware in the silicon domain is concerned. So I mentioned earlier the RISC-V instruction set architecture. There's a company called Sci5, which has been founded by many of the same people who developed the RISC-V instruction set. It's a proprietary organization in that they are money making, and they do sell proprietary chips based on the RISC-V architecture, but they also produce a lot of open source hardware as well. They have, I should have checked actually, but I think certainly last time I looked, they had $125 million invested in them. So it's still a long way to go before open source hardware reaches the economic impact of open source software, but there's a number of organizations who are taking it very seriously. Other big companies include Western Digital, who've developed something called the Swerve core as well, which is also based on RISC-V. And there's another project called the Open Compute project, which develops a lot of what they call open hardware. I think I won't go into that in detail, but there is a question as to precisely how open that hardware is. But that's designed to produce hardware for use in data centers, and that includes everything from the design of the cabinets, the design of the power supplies, through to software that's used to interconnect and monitor the various servers and so on that are used in there as well. So there's a lot of economic activity going on in the world of open hardware currently. So what licenses are being used? Well, a lot of people are using content and documentation licenses for open source hardware. So I mentioned the Creative Commons suite of licenses before. Some of them, as I said, are suitable for use to a degree with open hardware. Some of them simply not. So, for example, we have CC0, which is basically as close to giving the design away for free as you possibly can. It's equivalent in countries that recognize donation to the public domain as donation to the public domain. In a lot of other countries, you can't dedicate things to the public domain, so you're always going to have to license them, but the license is basically as free as possible. So if you're using any materials under CC0, then you'll get as many rights from the person granting those rights as you possibly can. Slightly more restrictive is CC BY, which means that you can use the design for pretty much anything. You can modify it as much as you like, you can redistribute it, etc., etc. But you also have to keep an attribution in there saying if there's any copyright notice you need to retain, then you have to retain that copyright notice. And then CC BY SA is the reciprocal copyleft version of the license. It's called SA because they call it share alike in the world of Creative Commons. And all of those can be, to a degree, used for open hardware. There are other licenses within the suite that you can't use for open hardware. We've already talked about NC, which is non-commercial, and there's another one, ND, no derivatives, which means that you can't actually make any changes. And you'll recall that one of the requirements for freedom or openness is that you're able to make changes to something. So, but any of those three licenses, CC0, CC BY, or CC BY SA, are all suitable for open source hardware. People also tend to apply software licenses to hardware as well. You'll be familiar with GPL, LGPL, MPL, Mozilla Public License, BSD, MIT, and so on. So all of those have been used with greater or lesser success with open hardware. But we do recommend that people use a specific hardware license, such as TAPA, or ideally the CERN Open Hardware License family, and also alternatively SolderPAM. And there's a number of rarer other open hardware licenses as well. And I touched on Open Compute Project earlier. It's an open license, but I wouldn't say that it fulfills the requirements of open source hardware, because it's basically a specification license in that it says that if you comply with this license and you fulfill the various specifications, then you'll get the benefit of patents which have been licensed. But if you deviate from the specification, then you don't get the benefit of those patents. So I'm not going to go into that in great detail, but essentially, it's questionable whether that fulfills the complete definition of whether it's an open source hardware license or not. But it has its place and it's a very worthwhile project. So that's not a negative thing necessarily. So I think I can probably, we started a little bit late, didn't we, Gaston? So I can probably carry on for another sort of couple of minutes on another few issues, and then we can move on to a question and answer session. So I was going to talk a little bit more about the CERN OHL and how that works. So the latest version of CERN OHL is actually a family of 3 licenses. And we decided that in the same way as with software, there is no one license that's suitable for everything. People have different requirements, that it would be helpful to provide a family of licenses within the CERN OHL as well. And we talked about Creative Commons earlier, and Creative Commons is also a family of licenses. So the strongest of the CERN OHL variants is called Strong, and that is a copyleft license. And if a product contains a strong component, so a component which is licensed under the strong variant of the CERN OHL, then that basically means that the whole of the product has to be made available, or the designs to the whole of that product have to be made available under the strong variant of that license as well. And that's broadly equivalent to the previous versions of CERN OHL. So if you'd used a version of CERN OHL prior to version 2, then that is equivalent to CERN OHL S, the strong variant now. And that's equivalent to licenses in the software world like GPL, for example. The weak variant is also a copyleft license, but the copyleft effect is that much weaker. And if the weak design is modified, then the design documents for that part of the design have to be released under the weak license, but not the rest of the product. So this enables you to mix proprietary components with with copyleft components, and it's only if you're modifying that copyleft component will you have to release the source, the design materials for that particular modified components. You don't have to provide any design materials for the other components as well. And then the weakest version is called permissive, and that essentially allows you to do anything with the code or with the design. You can combine it into other products without any problem at all. The only thing that you do have to do is, if you do distribute a component which contains the permissive variant, any subcomponents that are the license of the permissive variant, then you have to make sure the attribution requirements are fulfilled. So you have to let people know that it contains CERN OHL materials and provide any copyright notices, etc. But otherwise, you don't have to provide any of the underlying design, etc. Other characteristics of the CERN OHL. So we've talked about the use of available components. It's also been optimized for use in chip design. I mean, it can be used for mechanical designs as well, and frequently is, but it's been optimized for use in chip design, because one of the issues that I touched on earlier is, if you're designing a silicon chip, there are very few open source tool chains available, and the proprietary tool chains will typically contain components as primitives. So, for example, there may be a subcomponent if you've got a memory array, for example, that will typically be provided as a subcomponent within one of which is available to you when you're using that particular sort of proprietary tooling. You won't necessarily know exactly what subcomponents that memory array consists of, and as a result, you won't be able to provide the source material for that particular memory array. But as long as the tool chain is generally available, even if you have to pay for it, then that means that you can use that within a CERN OHL design. It's not an ideal situation, but it just addresses the reality that if you're doing chip design, you are in all probability going to be using proprietary tools. So if we just talk a little bit about the economics of open hardware, how can we monetize it? Well, obviously you're able to sell the actual hardware. People are used to paying for atoms. They may, especially with the prevalence of open source software, be less used to paying for bits. So a classic example here is Arduino. Their products are all available as open source hardware. People pay Arduino to provide them with the physical microcontrollers. And that's not a problem. People are used to doing that. Because it's open source hardware, it means that third parties can come in and they can use the Arduino designs to produce their own designs, and that happens pretty frequently. But Arduino is not unhappy with that happening because people believe that the Arduino name stands for good quality control. If you buy a product directly from Arduino, you know that it will definitely meet the specifications, you know that it'll support it, you'll know that it's been manufactured under control environment, etc. So people are essentially paying for the product, but they're also paying for the comfort that a product which is being provided by the Arduino organization or is approved by them has gone through certain quality control procedures. So the value to Arduino really from a financial perspective is in the use of their trademark there. If you're providing open source hardware, you can also provide training and consultancy around the designs. And thirdly, one of the particular aspects that arises is also certification of provenance and quality. So it would be open to Arduino to license their name to third parties producing various aspects of their products, if those third parties have been through a quality control and certification procedure, so that you know that if you purchase products from those third parties, you're going to be getting a good quality product because it's been assured by Arduino as well. And then finally, and this increasingly applies in areas like medical and pharma and automotive, where in order to monetize a product and put it onto the market, it has to go through a certification process. You can also charge third parties for providing them with all the materials that you need to assist them to go through the certification process so that they're legally able to put those products in the marketplace as well. So a few other issues that we're considering about at the moment: liability. Who is liable for the provision of an open source hardware design? All open source hardware licenses, in common with open source software licenses, will have a disclaimer of liability in them saying that you use this design at your own risk. It's questionable in some jurisdictions how effective that particular disclaimer is, because lots of jurisdictions have laws saying that disclaimers of liability are only effective in certain circumstances. But broadly speaking, if you're receiving an open source software component or an open source hardware component design, and you get it under one of these licenses with a disclaimer, you'd like to think that the courts in any jurisdiction would say, well, you got this design for free, so it's not fair for you to then be able to raise a claim against the designer if you've got a problem with it. And in that case, if you wanted to have some sort of relationship with the designers so that they are liable, then you'd want to have a separate agreement, and then you could sue under that agreement. Typically, you would then have to pay for having that particular right, and you get questions of insurance involved, etc., as well. So one of the fundamental questions is, who should be liable if a product is placed on the marketplace? I mean, clearly, from a consumer perspective, if you receive a defective product from somebody, then you should be able to claim against somebody if that product injures you. That's a fundamental part of consumer law. The question is, who in the supply chain should be liable? And it would typically be the person who places the physical object onto the marketplace, and then they would have to cover their liability off. Either they would typically get insurance to help them do that as well. So at the moment, I'm working with a number of academic institutions thinking about whether placing the designs into a foundation might help, because if there is a potential claim that tries to circumvent these various disclaimers of liability, then people would possibly be reluctant to sue a foundation, and especially if the foundation has no money, then that would be a big disincentive. So that would make the designers less of a target. We've talked about maybe there should be some sort of insurance scheme as well. And then another issue is the question of how do you maintain quality down the supply chain. And we're working with some people at the moment who are producing open source equipment for use in a disaster relief scenario. So this typically would involve, for example, in an earthquake zone, it will be people need to be able to have access to clean water, and therefore they're involved in designs for things like pipes and valves and junctions and so on that you would use in a water distribution system. And ideally, you would want these particular items to be manufactured as locally as possible so they don't have to be shipped in from a long distance. How do you maintain quality? And rather than having a centralized quality control system, maybe there's another system which can be used where organizations certify that they comply with various standards, that they understand the various issues, that they have various training, etc., in producing the quality materials themselves. I'm not going to go into that in any detail, but there's an existing quality control and compliance framework called OpenChain in the world of open source software, and maybe that can be adapted for use in hardware as well. So let's wrap up by summarizing. Essentially, open source hardware is much less mature than open source software, but it's catching up. And there are similarities between them, but you've also got to be aware that there are big differences. So, for example, in terms of IPR and in terms of the development processes, what is needed to develop open source hardware as opposed to open source software. Some of the basic definitions are not quite so clear in the world of open hardware as they are in the world of open source software. And the licensing situation is more complex because many more intellectual property rights potentially involved. On the other hand, a great advantage that we have in the world of open source hardware is there are many fewer licenses. So we don't get this problem with license proliferation that we have in the world of open source software. People are much more likely to choose from a specific subset of licenses, and there are many fewer licenses, which makes understanding them much more straightforward. It's generally fairly dangerous to assume that what works in open source software will automatically work in open source hardware. Sometimes it does, sometimes it doesn't, and the softwareness of a particular piece of hardware may have something to do with that, but we don't really know the answer to that yet. The real world has much more of an impact with open source hardware. We're making things out of atoms, and atoms are much more difficult to deal with than ones and noughts are. And it's unclear what business model currently works best in the world of open source hardware. I mean, we're not clear in the world of open source software, but at least there are many more that have been tried and tested. But the situation is much more unclear in the world of open source hardware. And there's a lot of study to be undertaken. And that is what we are attempting to do at the moment. So with that, I will say thank you very much indeed for bearing with me. I hope that answered some of the questions that I was asked to look at. And now I would be very happy to take any questions that people may have. So if you, I don't know, Gaston, what facilities we got people to do that, whether they can unmute themselves or whether they want to put the questions in the chat.
Yeah. First, thank you very much for this great introduction to open source licenses. And yeah, anyone who wants to ask a question can unmute themselves and just talk, or they can raise a hand and then we can. Yeah, I think Nico has a question.
I have lots of questions actually. But I don't know, actually very broad questions as well. So perhaps one to start is, when is it most beneficial to work openly in hardware? In which context? Which kinds of projects? I can give you an example. There was I heard once that the most impactful open source projects, the most impactful opportunity for openness in software projects is when there are no equivalent software projects in the market. That is one case. But perhaps you have better ideas for hardware.
Yeah, that's a really good question. What is, I think, with the last couple of years we've been living in the world of COVID, and that developed an awful lot of interest. An awful lot of people, they had equipment like 3D printers, and they were very interested in making available things like respirators and personal protective equipment and so on, some of which is quite simple to build, and some of which, but the specifications are important, and quite a number of communities sprung up around those, and that really highlighted one thing, is that the ability of the design and build and test cycle to impinge is quite important there. So if you have something that's a simple hardware design that can be reproduced very quickly, and if you need to change it in some way in order to make it better suited for its environment, that seems to work particularly well in the world of open hardware. And that's when you get this sort of early stage development process. So when you're talking about an open development process as opposed to a release when ready process, that means that you do get people collaborating at a fairly early stage in the design. And I think, as has been demonstrated with software, you do tend to end up with a better product if you do that. So facilitating that particular process, which can happen, with fairly simple hardware designs, particularly things like respirators, for example, has proven to be pretty beneficial. I mean, ideally, you need to have a community that is that has a particular goal, that wants to get something done, that is motivated to get something done. And that was definitely the case with a large number of these COVID related projects. And because it's more difficult for people to collaborate on designs that are at the harder end of the spectrum, that becomes so much more important, this idea of motivation, because automatically there will be a whole number of people that may want to get involved in a particular project, but are not actually able to because they don't have the equipment, they don't have the 3D printers, and so on. And that is always going to be an issue as far as hardware is concerned, as opposed to software. So I think, and one area where it is proving to be successful, and a lot of you will be aware of this, is in the idea of in academia, where you're creating test equipment, for example, for use in laboratories, and this is something that can be done very effectively, because you have a bunch of motivated, competent people who will have access to a lot of the equipment that is required to make these particular tools. They'll be familiar with the idea of collaboration, and they will also be faced with cuts in academic budgets. Every single university in the world suffers from that, and also the very high prices that some of the commercial providers will provide the same equipment for. So for all of those reasons, that is something that can prove to be pretty successful when you get a bunch of researchers together in different laboratories around the world who all want a particular piece of equipment, like a centrifuge, for example. In that case, there's a lot to be said for working in the open hardware domain and working cooperatively in order to create something like that.
Great. I have one more question. Well, I have many, but I would like to ask one more. If there's if there are no other questions, of course. So I had a brief look at the CERN license, and it said that something about documentation. So what is included under documentation in the CERN license? Are instruction manuals included, like specifications for interfaces, design principles, or required knowledge?
So if you're, the first person to release the design of something under CERN open hardware license is under no obligations. So they can release anything they like, and they can release as much documentation or as little documentation as they like. And the expectation will be that anyone who downstream who then takes that design is going to take a lead from the original person who released the design, and basically produce things at the same sort of level of understanding, the same level of abstraction, and so on. So the lead is always going to be taken from the original person or team who released the design under the CERN OHL in the first place. But what we're keen to encourage is to make sure that people have all of the design documentation and instructions that they need. And this is actually another area where hardware differs to a degree from software, because if you release some software under an open source software license and you don't provide any instructions with it, then at least in theory it's possible for somebody to have a look at the source code and figure out what the software does. That's extremely bad practice, but at least it's possible in theory. With hardware, it might not be quite as straightforward as that, because if, for example, you're releasing something which is an analog radio, an analog, if it's an analog FM radio, then the chances are that's going to require quite a lot of setting up. And in order to make it work properly, because the tolerances of all of the components are not precise, you're not going to be exactly able to reproduce exactly the same performing radio as somebody else did, because some of their components are going to be of a slightly different tolerance. So you'll have to set it up. There'll be various components in there, like potentiometers, that you have to change slightly. And the setup process is something that's vital to get the functioning hardware at the end of the day. So we encourage people in that case to say, okay, just providing the design for how to make it is not good enough. We would like you also to provide all of the extra information that you're going to need to make sure that it works properly. And that includes specifications like, obvious ones like the sort of voltage and frequency that you need to plug it in to make it work. But it also, could be things like a setup procedure, or the types of fluids that it might need, specifications of oils and so on, that it might need. So the more information that can be contained within the documentation to make it useful to the end user or the person who is making it and then transferring it downstream, the better, basically. We didn't want to be sort of too prescriptive in terms of what's actually required, because that's going to vary significantly from design to design. But your instinct that you're going to require more information for hardware than you typically are for software is absolutely spot on. And I think that's something that we need to be very careful about in the world of open hardware as well. And it also means that, in the world of open source software, the people making the documentation are completely unfairly regarded really as sort of second-class citizens, and the real skilled people are the people making the code in the first place. I think we need to move away from that idea and say that in many cases documentation can be just as important as the code itself, and that's especially true in the world of open hardware, because just having the design is one thing, but actually being able to make practical use of design is something else, and you're likely going to need more information to enable that to happen with open hardware.
Well, that's great. Just a comment then. I think there is a boundary then where a company puts its how much you document is also how much where's your value, right? If you document absolutely everything,
yes,
then of course you make others free as possible.
Yeah.
But then you also facilitate innovation from other parts, right?
Yeah, that's very true. And also this also, I mean, people when we were drafting the CERN open hardware license, people did ask us, can we put requirements in there to make sure that the documentation is up to a certain standard, it does contain certain information, it does, and also other things like, can you make sure that the manufacturer is carried out in the most environmentally responsible way, and can you make sure that anyone who wants to make use of the design is treated ethically, and that the design is not used for bad purposes, etc., etc., etc. And while each one of these requirements, is objectively a good thing in their own terms, what is essentially an IP rights license is not the best place to enforce those. So, we are aware that there are certain obligations that we cannot be too prescriptive about, but people should also sort of consider them separately well. And this is something the Open Source Hardware Association is actually better placed to deal with, because they can have a number of certifications. And so, for example, they could certify, I mean, they're not doing it at the moment, but we have talked about this. They will certify whether something is open source hardware or not, but they could also certify that it's a green design, for example, or they could certify that it's designed to be easily accessible to the end user so that it can be repaired easily in the future, and so on. So there's a number of different criteria that you could apply to a design, but it's not necessarily the best place to have those requirements within the license itself.
Thanks. I have a question about the monetization of open source hardware. I mean, it's pretty clear for a small company, say, or a company that sells atoms and sells also the quality and has the all the things. But in terms of startups, for example, who are looking for investors, and sometimes it makes it's a bit difficult to convince all the investors to invest money on open source hardware, because they just want to live from a rent of a patent. They don't want to make a living of selling atoms by selling atoms, but just by selling ideas. So how can these companies convince all the venture capital, for example?
That's a really good question, and there are a number of venture capital firms which are a little more understanding of open source than others. But ultimately, for any of them, you're going to have to convince them why, well, if you make your designs publicly available, doesn't that mean your competitor can take them and start competing with you immediately? So you've got to convince them that you can differentiate yourselves from your competitors in other ways. Now, to be completely cynical, I have come across clients who will go ahead and apply for patents for various aspects of their designs on the basis that the patent, even if it's only patent pending and hasn't been granted yet, is going to be, it's something that the venture capitalists are more happy about, even if their intention is they're going to license it freely later. So I do have clients that do that. But the answer is there's no complete answer to that at the moment. It may be the case that they're saying, okay, we're producing, and this applies to software as well as hardware, we're doing what we're doing on a sort of hybrid model, that some of the stuff that we sell will be open in order to generate a community, and we will help the community to and we will leverage what they produce into our proprietary designs, which we're selling alongside. So an organization like Sci5, for example, which sells RISC-V processors, both proprietary ones and ones that are available under an open source license, is taking this sort of view, and they've got a significant amount of investment. But one is suspects that the investment is on the basis of the actual revenues generated from the proprietary designs they're selling, and not necessarily the open source ones.
I see. Okay, thanks. And another question I had is, so when you are designing a hardware and you want to apply for example, a CERN license, you mentioned that, okay, you also have to check for patents, that you can be infringing some patents, right? So so can you summarize how would be the process once you have a design and you want to apply a license? What would be the process in order to be able to do that?
I think that, when it comes to sort of choice of license, the first thing that you would consider is what you're trying to achieve here. And so that you think about the audience of the people who will take your design, what they're going to do with it. And if, and I call it really the distinction between sort of freedom maximization and use maximization. So if you want to make sure that people who use your design are going to make the design available to third parties, and any modifications are going to be made available to third parties alongside all the design documents. So essentially you want to force people to build a community around it. Then you would use a reciprocal license, like CERN OHL-S. If on the other hand, you don't really mind too much as to what happens to your design once it's released to the world and it could be incorporated into proprietary designs, and what you want to do is to get as many people as possible using it, whether under a proprietary license or not, then you would use a permissive license. And it's not obvious which is the best solution, and it will vary from so in the world of open source software, we have the Linux kernel, which is released under a copyleft license, and that's hugely successful. We also have the Apache web browser, which is released under a under a permissive license, and that's also hugely successful. So it's not immediate. You can't obviously say that one sort of licensing model is better than the other, but they do tend to develop different communities around them. Different people have different views as to which is more appropriate. So that's probably the main criterion that you would look at. Just coming to the other part of your question about patents. This is a sort of perennially difficult problem, and in order to check to see whether your design is going to infringe any patents or not, it can be an expensive process. It's not something that we do as a law firm. It's something that you go to a specialist patent agent to do, and there are patent search organizations that will do clearance searches for you as well. But yes, that is an issue. It's equally an issue whether you're producing open source software or hardware, or proprietary software or hardware as well. The only slight issue is that with hardware, it's going to be sort of more obvious whether you're necessarily infringing, because you can actually, you know, look at the physical object, and if it's open as well, you can look at the design, and from the design you can determine whether something is likely to be infringing or not. But there's no sort of obvious solution to that problem, unfortunately.
I see. Okay. Thanks. Okay, I don't know if there are more questions.
If you want, I have a couple more, but we can talk later. If not,
we have time for
what you prefer.
It's okay.
Yeah, I'm happy to go on for a bit longer if people want me to.
Well,
Great.
first, I would like to invite someone else to some other participants to ask questions, so I don't take up the whole time. Just a second, I'll leave.
So, any other question? Just go ahead, Nico.
Okay, great. So, where's the boundary exactly for a strong component in CERN terms, in the CERN OHL terms? So, are interfaces with strong components affected? Like for the suspension example, you have to release the whole car or just the interface for the suspension?
Yeah. So the general rule is that if you have a documented interface, then what is on the other side of the interface is not affected by the copyleft reciprocal requirement. So no, I mean you're absolutely right. The key is the interface, whether it's an electrical interface or whether it's a physical interface. What is on the other side of the interface does not need to be released under the specific license.
So it would be a good idea to document the interfaces so other projects can reuse our project in any way they want to without having the need to. Okay.
Yes, exactly.
That is a good thing.
And what I recommend, and if you look at the FAQs on the CERN OHL website, it follows this advice, is if you're making something under a number of different subcomponents. So for example, if you're designing a PC, so you can have the case, and you can have the main processor board, and then you can have plug-in boards, and you can have the power supply, and so on, rather than trying to release the whole lot under a single license. It's actually much better to look at each component separately, license them separately under their own license, and then to have, so in that case, you would have a design for the power supply, and you'd have the design for the main motherboard, for example, and then you would have an overarching design, which you may also want to release under the CERN Open Hardware license, that just is basically a block diagram that says, this is a power supply, this is a motherboard, and this is where you plug it in, and the interface is just your standard power interface that you've defined. So the more that you think in terms of modular designs, the better. I think the better the whole CERN OHL ecosystem is going to operate.
Okay, great. Thanks, Andrew.
Okay, well, I'm very happy to take any more questions if anyone has them.
Well, I do.
Nico, okay, go for it.
Well, there's just some rumblings in my head for some time, right? More of a discussion, perhaps. To me, when an open source project is released with certain application or a certain field, to me it's like the value moves away from intellectual property, moves towards the manufacturing know-how on the quality of the products, and etc. But so what is closeness worth in this context? Once you have an open or many open projects in the field, is closeness worth something in particular?
So sorry, closedness.
Yeah, like closing a design or working in a closed way, not sharing the designs, basically.
Yeah, no, that's a really interesting question, and I think we may have to sort of take a step back in terms of what do we mean by openness. I mean, I touched in the talk on the fact that it's not quite as straightforward in the world of hardware than it is with software, and I could certainly there are plenty of organizations that have taken open source software licenses and they have technically complied with them, but actually the end result hasn't been particularly useful because it's not, you could call it a loophole, you could call it an exception, but they're not really complying with the spirit of the licenses. And I think you've sort of touched on something pretty important there, in that it would be quite easy for an organization to comply with the full legal requirements of the CERN OHL, but not actually provide all of the other information and the know-how and manufacturing experience and so on that an end user is specifically going to need to make the full use of the product. So I think all I can say is it's something that we actually need to be aware of, that it's an issue, and encourage organizations to be good members of the open hardware community. Whether you can actually force them to do that, I think you probably can't. There's a limit to what you can achieve with a license.
And one last one, if you want. We were discussing the other day with Gaston that perhaps engineers would prefer to work in open projects, because when they finish, anyone would like to say, look, I did this and I can keep working with this after I'm done here or whatever, right? So, is this true? Okay,
Definitely. Yeah, and I think that whether you're a researcher or whether you're working in a commercial organization, you're always going to prefer working in an open environment, because I think the most important thing about open technologies, whether it's open source software, open hardware, open data, is minimal amount of friction. And because basically, if you're interested in making the world's greatest ventilator, you just want to be able to get on with making the world's greatest ventilator. You don't want to have to worry about intellectual property rights, whether you have permission to do this, whether you can get in touch with somebody else that might have a solution to the problem and talk to them about it freely and so on. That's what we all want to do. So that is what open design methodologies enable you to do if they're operating properly. So it's I think it's preferable for anyone really to want to work in an open environment.
Yeah, that's very interesting, and I think also it can be another reason in order to convince people that the good things about open technologies. I mean, one thing I wanted to ask is, I mean, it's also difficult to convince people, for example, in the universities working on the research and development departments of university, who are making, I mean, the connection with industries and the connection with, I mean, to transfer the knowledge generated in the universities to industries. I mean, they all work with the proprietary way of doing things. So what do you think can be done in order to make these people more, I mean, to introduce these people to these open technologies, open licenses?
Yes, no, that's a very good point, and I deal with technology transfer offices fairly frequently, and you're getting an increasing number of people who really do understand open technologies. And but as you say, a majority of them, I mean, the way that they operate is, they're mandated basically to take the university's IP and to try to monetize it for the university. And from their perspective, that means getting as many patents as possible and selling them. So I think there's an awful lot of sort of education that needs to be done. I mean, there are some, CERN, for example, is excellent at doing this. And they will explain to people why they believe that it's important that they do collaborate with other organizations on an open basis. And one of the activities that we recommended when we did the European Commission study a couple of years ago was to set up open source centers of excellence, was to set up open source program offices, which are basically, or sub-organizations within an organization that understand and can provide information about open source and why it's a sensible and good methodology. So I think the message is sort of starting to reach out the technology transfer offices. I mean, about 3 years ago, I was at a conference of an association of university technology transfer offices. And you're right, a lot of people, they don't really understand the concept of open source, but I'd like to think that I helped to explain that to them. And I am coming across more and more people within the technology transfer offices who do understand the benefits of it. So, we can provide them with examples where open source has been successful. I mean, for example, the release of the RISC-V instruction set architecture by Berkeley, University of California, Berkeley, for example, is another one of those. Listen to respected organizations like CERN, who will tell you why they think open source is a good approach for them, and so on. But it's a challenge. It is a challenge.
But how do you compete with how do you argue against the argument about I mean, they want to make money. I mean, they want to receive revenues from the patents. I mean, how do you argue against that with the technology transfer?
Well, there's a number of ways you can do it. I mean, we talked about the people wanting to work in open technologies. So if you want to attract the best staff, the best researchers, etc., you're going to have a much greater ability to do that if you are prepared to work in open technologies. You can also take one step back and say, and this will depend on the funding of the particular university, but also is it reasonable that if public funds are being expended on the creation of knowledge, then that knowledge shouldn't be made available to everyone. And that's sort of very much the line that CERN takes. It's basically a sort of public money is public code approach. So that's another opportunity. We then have some universities I'm talking to. They are thinking in terms of okay, should we set up our own commercialization offices that think about whether it's better for us to collaborate with other organizations on an open source way, but at the same time we are looking in so that's a list of various sorts of monetization. I mean, there's one university that I'm talking to at the moment that is thinking of setting up its own foundation that potentially has a commercialization arm, and the commercialization arm then can provide access to consultancy, can provide access to the dossier of information to enable medical devices to be brought to market, and so on. But it does mean that the technology transfer offices, they have to go one step further than they normally do. It's not just a question of negotiating the licenses of patents. It's thinking in terms of the business models, and thinking, okay, should we set up an organization whose specific goal is to monetize what we're producing, even though it's open source. And so that is going to require a fair amount of investment to do that. So it's sort of interesting that universities are prepared to talk about it. And I think as soon as we start to see some of these organizations appear, and if they're successful, then it's going to be much more attractive to other organizations to do it as well. But I'm hoping that this particular organization that I'm talking to is that the university I'm talking to is going to be able to set up a commercialization wing, which is then very successful, and that can be then emulated by other universities worldwide.
Great. Thanks. All right. I don't know if there are more questions. If there is no more question, then we would like to thanks again, Andrew, for this very interesting talk and discussion. I mean, it was great to have you today here. And thank you all to all the participants in YouTube and also in Zoom to join this seminar. I think Nico has raised the hand.
Yeah, yeah.
No, I was just clapping with an emoji.
Okay.
Fantastic. Yeah, well, Gaston, thank you so much for inviting me. It's been a real pleasure. I think there have been some fantastic questions. I'm always happy to answer any more questions. So, if anyone wants to email me or sort of get hold of me on any other mechanisms they can find, then please do. I'm always happy to engage. It's a fascinating topic.
Okay, thank you very much, and thank you
Thank
for
you
your
very much, Andrew. Yeah.
Thank
Okay,
you.
bye-bye, everyone.
Okay, goodbye.
Thank you, Andrew.